So thank you for the invitation to speak. So the support theorem of NGO is a key statement in his proof of the famous fundamental lemma of Langlands and Shellstad, and it is a statement about the relative cohomology of the Hitchin fibration. And in the talk, I will explain this statement in the particular case of the group GLN. So this is a statement about the relative cohomology of the elliptic part of the Hitchin fibration. And I will also explain in my talk how to extend this statement to the whole Hitchin fibration, still for the group GLN. And this extension is a joint work with Gérard Lomont. So let me begin by reviewing what is the Hitchin fibration. And first, let me begin by giving the definition of Hitchin bundles. So the situation is the following. We fixed an algebraic closed field K, and we fixed C, a smooth, connected, and projected curve over K, and G will be the genus of C, and I will also fix an effective divisor G on the curve of degree denoted by small d. And I assume that the degree is bigger than 2g minus 2. So we will see at one point of the talk that this restriction will unfortunately appear, because the case of a canonical divisor is a very interesting case, in particular from the point of view of non-abelian Hodge theory, but I have almost nothing to say in this case. So I assume that the degree is bigger than 2g minus 2. And definition, Hitchin bundle over C is a pair E theta, where E is a vector bundle over C, and theta is a homomorphism of OC module from E to E twisted by D. That is E twisted by the line bundle associated to D. So theta is a twisted homomorphism, or twisted endomorphism. So that is the following datum, and we have the following invariants. Of the pair E theta. First, we have the rank of the underlying vector bundle. We have the degree of the underlying vector bundle. If E is not 0, we have the slope, which is the ratio of the degree by the rank. Okay, so this is just for the underlying vector bundle. But attached to the twisted endomorphism, we can define a trace in the following manner. First, I can consider the identity section of the endomorphism of E. Then I can use theta to go to E times E dual twisted by D. And then I have a canonical map from E instance, it's dual to O, and then I go to O of D. So in this way, I have defined the trace. This is a section of O of D. And moreover, I can consider the exterior power of theta. This is an Hitchin bundle associated theta go to E twisted by D. So I can take an exterior power. So in this way, I get a new Hitchin bundle associated to the vector bundle, which is the highest exterior power of E. And the twisted endomorphism is attached to I of D. And so the trace of the highest exterior power of theta is a section of O of ID. So now, if n is a rank of E, I can attach a characteristic polynomial to theta, which is xn minus a1 theta x sine minus 1 plus minus to the n an, where ai so is a trace of the ith exterior power of theta, and this is a section of O of id. So this is a characteristic polynomial. And I can consider all the characteristic polynomial of a given rank. So let A, which means A sub n, it depends on the rank n. So this is the space, the affine space of all characteristic polynomials of degree n. So this is identified to the space of the section of O of id from 1 to n. And so by the Riemann-Roch theorem, this is of dimension n times 1 minus the genus plus n times n plus 1 over 2 times the degree of d. This is small d. Okay. To study Hitchin bundle, there is a very useful tool, which is the spectral curve. So due to Hitchin and also Beauville, Narasimhan, and Ramanan. So now I fix n a rank. Let me consider the whole space of the line bundle O of D. So by the Grothendieck construction, this is the spectrum of the sheaf of algebra sim of O of minus D. We have a natural projection on C. And you have a universal section of P of the pullback of O of D. And then, given an A, so which is xn minus a1 x to the n minus 1 plus minus n to the n. So this is a point, a characteristic polynomial of degree n. Then I can attach to the universal section and to the characteristic polynomial un minus the pullback of the section. So remember that A1 is a section of O of D. I can pull back it to sigma times U to n-1 and so on, plus minus to the n the pullback of AN. So this is a section of the pullback of O of ND. And then I define the spectral curve YA This is a Cartier divisor. Associated to the zeros of the section. So in this way, we get a curve on the whole space sigma. So it comes with a projection on C. So some facts about these spectral curves. First, it is always connected in our situation. But it is not always smooth. So YA not always smooth. But it is on an open set, on a dense open subset, A smooth in A. It is not always irreducible, sorry. But it is on a dense open subset called A elliptic. This is the open set of elliptic characteristic polynomials. That is characteristic polynomial which are irreducible at the generic point of the curve. So, and it is not always reduced, but it is on an open dense subset which are called RSS for regular semi-simple. So this means that the characteristic polynomial, say at the generic point of the curve is separable. So this is inside. So the elliptic locus contains the smooth locus, and the elliptic locus is contained in the regular semi-simple locus. Sorry? Yes, yes, yeah. And moreover, the morphism pi A from A to C is finite of degree n, is flat. And moreover, the direct image of the structural sheaf of YA is OC plus OC minus D. Plus OC minus 1 plus 1 minus n plus 1 D. So in particular, we can compute the arithmetic genus of YA. So this is the dimension of H1 of the structural sheaf. And then by again Riemann roll, we get this is H1C PA low star OY A. And this is, you can compute, this is n times G minus 1 plus n times n minus 1 over 2G plus 1. So you see that the arithmetic genus of the spectral curve does not depend on the choice of the characteristic polynomial. So let me give some examples of the kind of curves we may get. Example. So I will take C is P1. The divisor D is 2 times infinity. And the rank will be 2. And the complement of the infinite point as a define a card as the following. So first we can compute in this case the arithmetic genus of the spectral curves. So this is given by this formula. This is 2 times 0 minus 1 plus 2 over 2 times the degree, so d is 2, plus 2 plus 1. So we get curves of arithmetic genus 1. And let me take a characteristic polynomial. So let me take A in A. I will take a characteristic polynomial of degree 2, but with the first coefficient is 0. So minus A2. And A2 is a section of O of 4 infinity. So this is an element. This can be identified to a polynomial in X of degree less than 4. So let me assume that A is exactly of degree 4. So this means in particular that the morphism pi A will be étal over infinity. So what happened in this case? So first assume that A2 has 4 distinct roots. So then YA will be smooth. So we get an elliptic curve, something like this. So if A2 has only one double root, so we get a curve with a node. And if A2 so for example, here to have 4 distinct roots is an open condition on this space. So you get the smooth locus. If A2 has one triple root, then we get a singularity cusp. And if A2 belongs to the elliptic locus, so that means that the YA is irreducible, so such as in the previous example. if and only if A2 is not a square. Is not a square. This is an open condition. And if A2 has 2 double roots, then we get 2 pi1 which intersect transversally. And also if A2 has a say at the opposite, if so it does not satisfy this condition, but if A2 is a 0, when we get a second pi1. In this case. So these are the picture. Now the spectral curves are really very useful because of the following Hitchin-Bille Narasimhan-Ramanan correspondence. So H, B, and R. So for this, so let me fix a rank. Let eta be the generic point of C. And let me also fix a characteristic polynomial of degree n. So I get spectral curve y A. And then the fiber of the projection pi A over eta. So y A eta is a finite union of Artinian scheme. So one for each say irreducible factor. So A has say a decomposition as a generic point, say, and to each such factor Bi, I attach an Artinian scheme, and I will denote Ja the inclusion of the fiber over eta in Ya, and I introduce the following definition due to Chaudouard. So definition. So the point here is to introduce object on the Ya that which will correspond to each bundle of the curves. And the object will be torsion-free OY module of rank 1 over Ya that is coherent OY module F over Ya such that first the morphism from F to the push forward of the pullback of F on the generic fiber YA eta is injected. And second, the length of F at each generic point of YA is equal to the length of the structural sheaf. This is the condition we want. And so example, if YA is reduced, then such an F is, so I say torsion free, is a torsion free of rank 1, say on the smooth locus. Sorry? Yes. Yes. This is the condition of the rank, and this is the condition of the torsion. Yeah. So F is torsion free on the smooth locus, and thus locally free. Is not. Sorry. Yeah, thank you. So it is locally free of rank 1. So these objects are in fact related to Hitchin bundle in the following way. So let F such no Y a module, so torsion free and of rank 1. So now the push forward of F is an OC module, which is torsion free and thus locally free. On the smooth part, yeah. Yeah, on the smooth part. So this is locally free, and because F is of rank 1, this guy is of rank n. So this is half Hitchin bundle. So we have still to get a twisted endomorphism, but we have the universal section, which gives you a morphism from OYA to the pullback of O of D. And you get a morphism by tensorized by F. From F to F tends the pullback of O of D. And you can push forward. This gives you a morphism of OC module. And by the projection formula, this is nothing else but the push forward of f twisted by d. So this is theta f. So this is E sub f twisted by d. So in this way, I get a functor which associated to f Hitchin pair EF theta f. Okay.
Like the spectral curve is the eigenvalues of F is like the generalized eigenspace.
You mean?
So the spectral curve keeps track of what the eigenvalues.
Yes.
And
Yeah.
then this theta F, sorry, this F, your the OY oscillator system of the generalized eigenspaces associated with each eigenvalues.
This is the same thing at when you have a vector space and an endomorphism, you can interpret as a module over. I can also define, so this is Hitchin-Bille. I can also define the degree of such an object. By definition, this is the Euler characteristic of f minus the Euler characteristic of the structural sheaf. So this gives you the Euler characteristic of EF minus 1 minus the arithmetic genius of YA. And by Riemann-Roch, this is of rank n, so this is n times 1 minus g plus the degree of the vector bundle EF on C minus 1 plus q of YA. And this gives you the degree of EF plus n minus 1 over 2 times d. So I can state now the Hitchin-Bille-Ramanan correspondence. So this is due to Hitchin when the spectral curve is smooth. To Boville-Narasimhan-Ramanan when YA is integral. And Schaub in general gave a proof. So the functor is an equivalence between a torsion-free rank 1 OY module of degree, so let me fix the degree, of degree E plus n minus 1 over 2d, and the groupoid of Hitchin bundles of degree E, rank n, of course, and characteristic polynomial A. And so essentially, by the Caylor-Milton theorem, we can go in the other way. You can associate to such data an OY module of rank n, and the condition of rank 1 implies that you get for EF theta F the good characteristic polynomial. So let me just an example. So if F is a structural sheaf, then as we saw, the vector bundle associated to F is O plus O of minus D plus O of minus 1 plus 1 G. And what is the theta? Then we can write in matrix. So the twisted endomorphism is with values in this vector bundle but twisted by D. So in O of D plus O plus O minus D and so on up to O minus N plus 2 G, and this is given by 1 and we get A1 minus A2 minus 1 to the n an. So we get the usual companion matrix. This is so we know that it is really of a characteristic polynomial A. Okay, and let me just as an aside, as a remark, that we see that at each point such an endomorphism is regular semi-simple in the sense so it is an endomorphism of so at each point we have an endomorphism of a vector space of dimension n, and it is regular in the sense that the centralizer in GLN is of a minimal dimension n, and this is a general fact that is the twisted endomorphism is everywhere regular if and only if the associated OY module is free, locally free of rank 1. Yeah. Okay, so now I can introduce the Hitchin moduli space. So we could consider the algebraic stack of all Hitchin bundles, I of a given rank, even of a given degree, if one wants. But in this way, one gets a stack which is locally of finite type, but it is not of finite type, and it is also not separated. So we have to truncate the whole stack of Hitchin bundle, and for this we use the notion of stability. So let me remember that Hitchin pair E theta is said to be stable or semi-stable if for all subbundle of E such that F is stable under theta, not in the same sense, but in the sense that the image of F under theta falls in F twisted by D. So if we say that the pair is stable if for such bundle we have a slope condition. So remember the slope, this is the ratio of the degree by the rank. The slope of mu F is strictly smaller than the slope of E, or smaller or equal in the semi-stable case. Okay. So now we could work with the algebraic stack of semi-stable Hitchin bundles, but it is not separated. And if we take stability, sometimes it is not. It does not satisfy the existent parts of the evaluative criterion. So first good trick is to assume that the degree of the underlying vector bundle is prime to the rank. So n is the rank, E is the degree, and we will be in the so-called coprime situation where the degree and the rank are coprime. So in this case, we could define. So in this case, the stability is equivalent to the semi-stability. And instead of considering the algebraic stack of stable or semi-stable Hitchin bundles of degree E and the rank n, we will consider the coarse moduli space attached to this, and it has been constructed by Nitsure. So Nitsure, there exists a coarse moduli space of Hitchin bundles of degree E and rank n. Moreover, it is a smooth scheme over the base field K, and it is of dimension n square times d plus 1. Okay. And now we can interpret the characteristic polynomial as a morphism. So let me denote it by m, and if I want to be more precise, I will denote it by mn or mne if I want to recall the degree and the rank. And so we get a morphism by taking the characteristic polynomial of theta from M to the space, to the affine space of all characteristic polynomials. So I will denote it by F. So this morphism is a Hitchin fibration. And Nitsure also proves the following important theorem, that the morphism F is proper. So we have a fibration. The whole space is smooth over the base field, and it is proper over an affine space. And now we are interested in the fibers of the fibration. So Hitchin fibers. So let me first emphasize that the fibers have a lot of symmetry. So in the following sense, we can to a characteristic polynomial A in the base, we can attach the spectral curves, and we can attach the following Picard group. So let me denote JA. This is a group of line bundle over YA, but of degree 0 on each irreducible component of YA. So this is a smooth, connected, commutative group scheme. And each time I have a line bundle over YA and a rank 1 torsion-free OY module over YA, I can tensorize F with L, and I get a rank 1 torsion-free OY module, OYI module. So in this way, I get an action of JA on the fibers F-1 of A, because so in this way, a line bundle acts on Hitchin pair by Hitchin pair. I can, by the Hitchin-Bille-Raman correspondence, I can see it as a Hitchin pair associated to a rank 1 torsion-free OY module on YA, and so the action of L on this pair is E theta associated to L times F. So this gives you a new Hitchin bundle, and in fact, JA preserves the stability. Because we have imposed this strong condition, that is the degree 0 on each irreducible component. Sorry? It depends. Yeah. Okay. So let me look first at a case where YA is smooth. Then the Hitchin fibers by the Hitchin-Bille so in this case, the Hitchin fibers is identified with line bundles. So because YF is smooth, rank 1 torsion-free OY module are nothing else but line bundles, or identified with line bundles of some degree related to E, that is E plus n times n minus 1 over 2 times D. And this group acts freely and transitively on the Hitchin fibers. So this is a J8 torsor. So in this case, the Hitchin is smooth. The Hitchin fiber is smooth. But this will fail outside the smooth locus. And so we see that in this case also, the group JA is a Nabelian variety. And so the Hitchin fibers is identified with Nabelian variety. And over the smooth locus, the Hitchin fibration is a torsor over Nabelian scheme. Okay. So in this, no, not at all. Not at all, because all no, but no. They have all these guys have the same characteristic polynomial. So because okay. Remember, how do you build the theta? You start from the universal section, and then you tensorize by L times F. So you get something. And then you. Okay. And also, we get that the dimension of the fiber is equal to the dimension of JA, and this is the arithmetic genus. So it is independent of A. And in fact, we can show that all the Hitchin fibers have the same dimension. Yeah. The proposition for all A, the dimension so is arithmetic genus of our YA. So I don't recall the formula, but it is independent of A. So in fact, so it reduces to the dimension of the nilpotent cone, that is the computation of the dimension of the fiber of the characteristic polynomial x to the n. Okay. And also, when A is in the elliptic locus, that is when YA is integral, then the Hitchin fibers is identified with the compactified Jacobian. Due to Altman and Kleinman. And for such A, the compactified Jacobian is known to be irreducible. So in this case, the Hitchin fiber is irreducible. So to let me go back to my example. So back to the example. So with C is P1, D is to infinity, and the rank is 2. So if A belongs to the smooth locus, we saw that YA is an elliptic curve. So JA can be identified to YA, and the Hitchin fiber is also identified with JA. So in this case, the Hitchin fibers look like this. Sorry. And this identification is also we can say if A is in elliptic, again, the Hitchin fibers. So is identified with the compact effect Jacobian, and the compact effect Jacobian can be identified with the spectral curve itself. So X looks like in this way. And this is also true for, say, if YA is a 2P1 which intersects transversally, then again, the Hitchin fibers looks like the spectral curve. So you see, so this is, here we are not in the elliptic locus. So on the elliptic locus, the Hitchin fibers are irreducible, but it is not true outside the elliptic locus. So you can think in this example that of Hitchin fibers are simply the spectral curves. Okay, now I come to the problem of the relative cohomology of the Hitchin fibration. So on the smooth locus, things are very nice because the Hitchin fibration is a torsor under an abelian scheme. And so in particular it is smooth. So the relative cohomology is given by a local system. And so you know the cohomology, how to describe the cohomology of abelian varieties. Essentially, you have to give the cohomology in degree 1, and then you take exterior powers. But what we want is to have a description outside the smooth locus. And for this, we will use the decomposition theorem of Beilinson, Bernstein, Deligne, and Gaber. So this is, we will take a prime L, which is invertible in K. And the theorem is an assertion about the direct image. So the l-adic shifts given by the direct image of QL. So I will shift the things by the dimension of the whole Hitchin space. So this theorem says that this L-adic complex of sheaves is semi-simple in the following sense. First, it is up to shift isomorphic to the direct sum of its perverse cohomology sheaves, and the second, that the perverse cohomology sheaves are semi-simple, so they are direct sum of simple perverse sheaves, and in this way we can write this complex as a sum over all Zariski points of the base, the sum over some index of so YA is a closed immersion of the closure of the non-necessary closed point A in A, of the middle extension. So JA is the inclusion of an open dense set in the closure of A, of what? Of L A to the A, shifted by the dimension of A, and shifted by minus Y. And what is Ly? This is a semi-simple local system on UA. So that is, we have some closed subset in the basis. On some open subset of this closed set, we have a local system. We extend by the middle extension, the Goretsky-Kottwitz middle extension, to the whole closed set, and we push forward. And so this gives you a perverse sheaves, a semi-simple perverse sheaves, and we have some twist. And this described theoretically the complex of L-adic sheaves. So this is the theorem of Bellison, Bernstein, Deligne, and Gaber. So from this, sorry, thank you. So why? Okay, why does this theorem apply? Why? So because M is smooth over K of dimension M, and because the morphism is proper. Thank you. So let me define K as this complex. I don't want to rewrite this. So I can attach to K the so-called of K. I can attach the so-called of K is the A, such that there exists a degree for which the local system is not zero. And to any A in the so-called, I can define the occurrences of A as a set of degrees, such that the local system, the corresponding local system is not zero. And I can attach the amplitude of A as a difference between the max of the occurrences minus the mean of the occurrences. All these sets are finite. And the equation whose answer is Ngo's support theorem is what is what is so-called of K. So first we have some rather general observations, I think due to Goreski and McPherson. So observations. First, K. So we have a formalism of duality, Verdier duality, and because M is smooth, this complex concentrated in 1 degree is autodual, and so because F is proper, this complex is autodual. And this implies that if Y is an occurrency, belongs to the set of occurrences, then minus Y also belongs to this set. So you see that the mean is equal to minus the max, and also that the amplitude is 2 times the max of the occurrences. But now, if I belongs to, so occurs in A, then when you restrict your complex to the open subset UA of the closure of your point, then you see that in degree I minus dimension of A, this local system LAI appears in this complex, and in this way Li appears as a direct factor in the complex, in the direct image, in degree, so in which degree? In degree I minus the dimension of A plus the dimension of M. And thus, so this complex has no cohomology over 2 times the dimension of the fibers. So let me denote the dimension of F. This is arithmetic genus common to the all commons to all spectral curves. So we get that A minus dimension of A plus the dimension of M is less than 2 dimension of F, and we can rewrite this as I is less than 2 dimension of F minus dimension of M minus dimension of A. And this is also dimension of F minus dimension of the base. So this is plus the dimension of A. And so we get that I is smaller than the dimension of F minus the codimension of A in A. So this is for all I, so in particular for the max of the recurrences. And 2 times the max is the amplitude. So the amplitude is less than 2 times the dimension of F minus the codimension of the support in A. This is a first condition, a first inequality on the amplitude of A. And then we have another inequality, which is due to Ngos. This is the key, the technical key part of his work, the key technical point. So so remember that we have a group, commutative group scheme, GA, which acts on the fibers. And using this action, Ngo shows that there is some freeness property of the cohomology of the fibers under the cohomology or the homology of the abelian part of the group scheme. So the theorem gives the following inequality. The amplitude of A, so if A is in the circle, the amplitude of A is bigger than 2 times the dimension of the abelian part of GA. So we have a dévissage, a Chevalier dévissage of GA. As a quotient, we have an abelian variety. And as a kernel, we have an affine group, a commutative affine group. So essentially a unipotent group times the torus. And this is the dimension of this abelian part, which gives you a lower bound on the amplitude. And from this, we can play a game to first to get the theorem of Ngo. So the theorem of Ngo is about the relative cohomology over the elliptic part of the Hitchin-Bille. So remember, the elliptic part means that the spectral curves are reduced and irreducible. So integral. Okay, so let me state the theorem. So let me pick an element in the circle, which is also elliptic. Then A is a generic point of A. And let me give a sketch of the proof. So if A is in the circle, then we have two conditions on the amplitude. First, so we have first an upper bound. This is less than 2 times the dimension of F minus the codimension of the support in A. And we have a lower bound, which is 2 times the dimension of the abelian part of the Picard group JA. So to use this inequality, we have to compute this dimension. And for this, we introduce a normalization of YA. So when you have a line bundle on the YA, you can pull back it to XA, and you get a line bundle of degree 0 over XA. And this gives you a morphism, which is surjective. and which have a fine kernel. You can check, for example, if you have a node, then you get a GM, and if you have a cusp, then you get a GA, something like that. And this is an abelian variety, because XA is smooth. So now, so the dimension of J ab is the dimension of the Picard group of XA. And we can compute this dimension, so by a computation of tangent space, say. I forget the condition now. So here we have to put a condition on the characteristic of K. It must be 0. And I will explain why. Okay, so we have an exact sequence. Which gives you a long exact sequence in cohomology, not so long. You have the section of the structural sheaf of OY of YA. This is of dimension 1. The same thing for XY. This is of dimension 1. Here the curve is connected. So, because I assume it is elliptic. And then so you have these sheaves with a finite support. The dimension is the so-called delta Serre invariant. I call it delta sub A, so which measures the difference between the spectral curve and its normalization. And then you get H1 of OYA, H1 of XI OXI. So this is, and this is surjective, so this is the dimension we are looking for. So this is the dimension of the abelian part of the JA. And this is the arithmetic genus, the genus of YA, and this is also the dimension of F. So by this computation, we get that the dimension of the abelian part is equal to the dimension of F minus this invariant delta A. And now I use this inequality. So this inequality gives you that the codimension of small a in capital A is less than delta A. And here comes the restriction on the characteristic. So we have characteristic, we are in the characteristic 0 case. And in this case, Diaz and Harris have shown that the codimension, so if A is elliptic, then the codimension of A in A is always bigger than delta A. And in characteristic, in positive characteristics, we guess that this inequality should be true, but No one for the moment is able to prove this. So it is a problem of in positive characteristic. But in so characteristic 0, we have this inequality. And this implies, so this inequality and this inequality gives you an equality. So star is an equality. But remember, where does this inequality come from? We look at a degree. And we say that a local system cannot appear in degree bigger than the two times the dimension. So if there is an equality, this means that the local system LA appears in the sheaf of higher degrees. So this implies that the LA max of occurrences of A appears as a direct factors in R 2 times the dimension. But now we remember that we are on the elliptic locus. On the elliptic locus, the Hitchin fibers are irreducible, and this sheaf is simply QL. So you cannot have a smaller support than the whole A elliptic. So this implies that A is generic, is a generic point. And this concludes the proof with this crucial ingredient. Okay. So now, what is our extension with Lomond? So we get the following theorem with Lomond. So still, of course, we have the restriction in the characteristic. The so-called of K is simply the generic point of A. So outside the elliptic set, I remember that the Hitchin fibers are no more irreducible, but still we do not get any new support. So what is the argument? So sketch of the proof. So now in the proof, so we will see the special role played by the condition of the degree of the divisor. So let me denote lambda, the set of uples. So with so n is a collection of a rank, and M is a collection of multiplicities with the condition mi greater than mi plus 1 if ni is equal to ni plus 1, such that the sum over the rank times the multiplicity is equal to n. And to an element small lambda in capital lambda, I can attach a morphism phi lambda from the product of the elliptic open subset of the Hitchin bases in rank n1, n2 up to ns to A. So simply the characteristic polynomials a1 to as goes to a1 to m1 times as to ms. So this gives you a finite morphism. And A lambda will be the image by phi lambda of the polynomial such that AI is different from AJ if I is different from J. So if A is equal to phi lambda of A1 AS, then YA say the set of irreducible component of YA is YA I to the minus to the M sub I. And YA is the reduced scheme associated to the irreducible component. So simply, I fix a type of decomposition of my characteristic polynomial. And now, A is a disjoint union of all the locally closed subset A lambda. And so if I look at and you play N1 with S is 1, so this is simply the set of irreducible characteristic polynomial. This is my elliptic subset. And A1n is closed. This is precisely the locus where the characteristic polynomial are nf power of characteristic polynomial of degree 1. This is closed. Okay. So we will play the same game as before. So we have to show that if A is in the circle, then A is a generic point of A. So we have this general inequality. And once again, we have to compute the dimension of the abelian part of JA. So let me assume that A is in a stratum A lambda. And more precisely, A is phi lambda of A1 AS. So with AI is different from AJ. So first, I can consider Y associated to characteristic polynomial A1 times A2 times up to AS. So this is the reduced scheme associated to A. So I have a first map from JA to J A1 to AS. So I restrict to the reduced locus. I get a morphism from between my commutative group scheme, which is surjective with affine kernels, in fact with a unipotent kernel. And then the collection AY are the irreducible component of YA. So I can restrict on each irreducible component. Once again, I get a surjective morphism with fine kernels. And then I can consider the smooth and connected curves x, y, a, which is a normalization of y, a. So this is still the surjective, but now here we have an abelian variety. And this is with a fine kernel. So the dimension of the abelian part of JA is the sum of the dimension of the Picard group associated to the curve x, a, y. And so that's the dimension of JI ab. So remember, we have computed this dimension in the elliptic case. So because here, so now when I write A is phi lambda of some things, I mean that the A lambda are elliptic in a rank ni. So these are characteristic polynomial of degree ni, and I assume that they are irreducible, so they are elliptic. So this dimension, I have computed it in the previous proof. So this is the sum of the dimension of the Hitchin fibers in rank ni minus the invariant delta ai, so in a rank ni. So this is the third invariant for yai. But now I have the Diaz-Ariz inequality. That is the dimension, the codimension of AI in the Hitchin base in rank ni is bigger than delta and so this gives you a lower bound for the dimension of J ab. So this is bigger than the sum over the indices I from 1 to S of the dimension of the Hitchin fibers in rank ni minus the codimension of AI in the bases in rank ni. But now the morphism phi lambda is finite. The sum of the dimension of AI is equal to the dimension of the point A. So, the inequality I have started from, so star, gives you that the sum of I from 1 to S of the dimension of F and I minus the dimension of N of the Hitchin base in rank Ni is smaller than the dimension of F in rank N minus the dimension of n of A in rank n. But this is n times 2g minus 2 minus d plus 1. And this is, so we are in rank ni. This is ni times 2g minus 2 minus d plus 1. So this gives you that s minus 1 is less than n minus the sum over ni times 2g minus 2 minus d. So this is negative. This is positive. So this is negative. So this implies that s is 1. But if s is 1, so here this is in fact n minus n1. And here now this is, we know that this is 0. So here it must be 0 too. So n must be n1. That is, the multiplicity must be 1. But this means that A belongs to the elliptic set. And we are in the so-called Biot theorem. We know that this is a generic point. So this concludes the proof of the support theorem for the whole Hitchin fibration when the degree of d is bigger than 2g minus 2. And what happens for a canonical divisor? Well, the point is that in this case, the dimension of the fiber is exactly equal to the dimension of the base. So Ngo's argument work on the elliptic set, but outside the elliptic set, this gives you 0 less or equal than 0. So this means that you have equality. So you are in a case where the local system attached to A appear in higher degree in the commutative. So we know that each time we have equality here, this means that the local system attached to A and the maximal of the occurrences appears in top degrees. But now the Hitchin fibers are not irreducible outside the elliptic set. So there may be new supports. So what can we hope with this method is to prove that the top degree cohomology sheaf is locally constant on each stratum A lambda. And in this way, this method could give a bound for the so-called. That is, in the so-called, we can only find generic point of the stratum A lambda, but we can not get more than this. Another extension would be for other reductive, other semi-simple or reductive groups. In this way, so the theorem of Ngo is not true as it is stated, because we have really new supports, but they are nicely described and they fit in the theory of endoscopy of Langlands and Chaudouard. These are very nice pictures. But what must be true and what we have proved with Lomont is, at least on the regular semi-simple set, we get no new support. So we can hope that the same arguments give that the supports which appears in the so-called are precisely the supports Ngo found in his work. But still for the degree bigger than 2g minus 2. Thank you.